Hello everyone, I am Guruprasad Upadhya, HOD, Department of Mathematics, Canara Engineering College, Bantwal. So in this lecture, I am going to discuss the third module of the 18MAT21 Advanced Calculus and Numerical Methods, the second sem of VTU syllabus, the partial differential equations. So in that, formation of the partial differential equation by eliminating the arbitrary constants. In that I am going to discuss in this lecture. Now what is meant by partial differential equations? The partial differential equations arises in connection with the various physical and geometrical problems when the functions involved dependent on two or more independent variables, usually on time t and on one or several space variables. Normally, the simplest physical systems can be modeled by ordinary differential equations, whereas the most problems in fluid mechanics, elasticity, heat transfer, electromagnetic theory, quantum mechanics, and other areas of physics lead to partial differential equations. Now, an equation involving one or more partial derivatives of an unknown function of two or more independent variables is called partial differential equation. And order of the highest derivative is called the order of the equation. Some examples. So, important linear partial differential equations of the second order. One-dimensional wave equation, dou square u by dou t square equal to c square into dou square u by dou x square. And dou u by dou t equal to c square into dou square u by dou x square. This is one-dimensional heat equation. And two-dimensional Laplace equation, dou square u by dou x square plus dou square u by dou y square equal to 0. Now, before discussing the formation of the partial differential equations, first we will discuss some symbols used in partial differential equation chapter or notations. Suppose z is dependent variable, x and y are independent variables, z is function of xy. Now standard notations use it for the first order derivatives of z with respect to x and y. So P, that is dou z by dou x, or in short form you can write it as zx. So dou z by dou x is considered as P, the notation P. If it is function of x and y, then only use these notations. Q is dou z by dou y, that is partial derivative of z with respect to y. And second order partial derivatives, R is dou square z by dou x square, that means differentiate z partially with respect to x twice, or simply you can write zxx. Since P is zx, that means dou z by dou x, differentiate P partially with respect to x, you get R, that is dou square z by dou x square. So you can write R is nothing but partial derivative of P with respect to x. Similarly, T is dou square z by dou y square, that is zyy. Zy is Q, differentiate Q partially with respect to y, that is T. Now mixed partial derivatives, second order derivatives mixed one, that is S, dou square z by dou x dou y, or dou square z by dou y dou x, both are same. So you can write it as P partial derivative with respect to y, or derivative of Q, partial derivative of Q with respect to x, that is S. Now P, Q, R, S, T. P is dou z by dou x, Q is dou z by dou y, R is dou square z by dou x square or Px, S is dou square z by dou x dou y or Py or Qx, and T is dou square z by dou y square, that is Qy. So P, Q, R, S, T. So these notations, you can use these notations to solve the problems. Suppose z is function of x and t, then don't use these symbols, because in that case t is independent variable, not dou square z by dou y square. In that case you use the short form zx, zt, zxx, ztx or zxt or ztt, like that only you can use the notations, short form. Okay. Now, formation of partial differential equations by eliminating the arbitrary constants. If the given equation contains n arbitrary constants, then order of the partial differential equation becomes n minus 1. Just remember this concept. Suppose there are two arbitrary constants, then first order partial differential equation, you are able to obtain the first order partial differential equation. Examples: form the PDE by eliminating the arbitrary constants of the equation 2z equal to x square by a square plus y square by b square. The given equation is 2z equal to x square by a square plus y square by b square. Now differentiate this equation partially with respect to x and partially with respect to y. When you differentiate partially with respect to x, 2 into dou z by dou x, that is p. X square derivative is 2x by a square. And when you differentiate partially with respect to x, y is a constant, therefore it is 0. And hence, we get 2p equal to 2x by a square. And similarly, 2q equal to 2y by b square. When you differentiate partially with respect to y, dou z by dou y is q and y square derivative is 2y by b square. So here y square by b square. X, treat x constant, therefore 0 plus 2y by b square. And cancel 2, p equal to x by a square, or multiplying by x, px becomes x square by a square. And here also cancel 2 and multiply by y, qy equal to y square by b square. So x square by a square becomes px, y square by b square is qy, and using the given equation, substitute x square by a square and y square by b square in the equation 1, will get partial differential equation. And hence the required PD is 2z equal to px plus qy. X square by a square is px, y square by b square is qy. Now a square and b square is eliminated, and this is first order partial differential equation for this function equation. One more example. Form the PDE by eliminating the arbitrary constants of the equations ax square plus b square plus z square equal to 1. When you differentiate partially with respect to x and y, now you can write this as z square is 1 minus ax square minus by square, and differentiate partially with respect to x. Since z is a dependent variable, z square derivative is 2z into derivative of z. So when you differentiate partially with respect to x, it becomes 2zp. 2zp. Here derivative of 1 is 0, minus ax square derivative is minus 2ax, x square derivative is 2x, and by square derivative is 0 when you differentiate partially with respect to x, treat y constant. And similarly, 2z into derivative of z with respect to y partially, that is q. So 2zq equal to 0 plus 0 minus 2by. Now from these two equations, cancel 2, zp equal to minus ax. Now multiply both sides by x. So zxp or xzp equal to minus ax square. And similarly, zqy becomes minus by square. First cancel 2 and then multiplying by y, so you'll get zqy equal to minus by square. Now substitute minus ax square value and minus by square value in the equation. So z square equal to 1 plus zpx plus zqy. So that is the required PDE. Z square equal to 1 plus zpx plus zqy. One more example. Find the differential equation, that means PDE, of all planes which are at a constant distance a from the origin. So we know that equation of the plane in normal form is Lx plus my plus nz equal to a. A is length of the perpendicular from the origin to the plane. So here the constant distance a, that means here L, M, N are various arbitrary constants. As L, M, N are varies, so you will get different planes with the distance from origin is a. And we know that L, M, N are direction cosines of the normal to the plane. And L, M, N, it looks 3 independent variable, but only 2, because L square plus M square plus N square is 1. If you take L and M are independent variable, N, you can write N in terms of L and M, therefore only 2 independent variable or arbitrary constant. Therefore, first you differentiate partially with respect to x and y. L into 1 plus 0 plus n into p equal to 0. Similarly, when you differentiate partially with respect to y, 0 plus m plus n into q equal to 0. So, m plus nq equal to 0. Now, L is minus np, m is minus nq. And substitute this L and m value in this equation. So, you get nz, see this nz plus Lx, L is minus np into x minus npx minus nqy equal to a. But here to eliminate n in terms of L and m, we know that L square plus m square plus n square is 1 and L square becomes n square p square, m square is n square q square, and by taking n square outside you can write 1 plus p square plus q square is 1, n square into 1 plus p square plus q square equal to 1. Therefore, n square is 1 by 1 plus p square plus q square, or by taking only positive term, n is 1 by root 1 plus p square plus q square. So, this is n. Now, substitute the value of n here by taking n outside, z minus px minus qy equal to a by n. And n is 1 by root 1 plus p square plus q square. Therefore, z minus px minus qy equal to a into root 1 plus p square plus q square. This is the required PDE, partial differential equation. Next problem. Form the PDE by eliminating the arbitrary constants of the equation z equal to xy plus y into root x square minus a square plus b. Here a and b are arbitrary constants. Now differentiating partially with respect to x and with respect to y. When you differentiate partially with respect to x, p equal to y plus y into root x square minus a square derivative is 2x by 2 root x square minus a square, and derivative of b is 0. Therefore, p equal to y plus xy by root x square minus a square by cancelling 2. So, we got p equal to y plus xy by root x square minus a square. And when you differentiate partially with respect to y, q equal to derivative of y is 1 into x plus derivative of y is 1 into root x square minus a square. B is constant. Now from this second one, so you can replace root x square minus a square by q minus x. Substitute root x square minus a square equal to q minus x in the first one. Therefore, p equal to y plus xy divided by root x square minus a square, that is q minus x. Now multiply throughout by q minus x. pq minus px equal to yq minus xy plus xy. Minus xy plus xy cancels. So it becomes pq minus px equal to qy, or you can write pq equal to px plus qy is the required PDE. Next problem. Form the partial differential equation by eliminating the arbitrary constants of the equation z equal to a into x plus y plus b into x minus y. Now, before differentiating z partially with respect to x and y, you can rewrite this z as ax plus bx. Ax plus bx means x into a plus b, or a plus b into x, plus ay minus by, that is a minus b, b into y into a minus b. So you can write this z equal to x into a plus b plus y into a minus b. See this, ax plus bx, that is x into a plus b, ay minus by, that is a minus b into y. Now this becomes very easy to differentiate partially with respect to x. Therefore, dou z by dou x, that is p equal to 1 into a plus b, and when you differentiate partially with respect to y, q equal to 1 into a minus b, and hence a plus b becomes p and a minus b is q. Now substitute this p and q here. The required PD is z equal to x into p, or px plus qy, because a minus b is q. So this is the required PD. Next problem. Form the PDE by eliminating the arbitrary constants of the equation x square by a square plus y square by b square plus z square by c square equal to 1. If we consider there are three arbitrary constants, a square, b square and c square, then it requires second order partial differential equation, because three arbitrary constants, and hence when you differentiate partially with respect to x, we get 2x by a square plus 0 plus 2z into p by c square equal to 0. 2x by a square plus z square derivative with respect to x is 2z into dou z by dou x, that is p by c square equal to 0, because when you differentiate partially with respect to x, treat y constant means this derivative is 0 and here derivative of 1 is 0. Now cancel 2, x by a square plus zp by c square equal to 0. Now since second order partial differential equation is required, differentiate this partially with respect to y. Now differentiate x by a square plus zp by c square equal to 0 with respect to y. When you differentiate partially with respect to y, derivative of the first part is 0, because it is constant, x is constant when you differentiate partially with respect to y. And use the product rule to differentiate zp with respect to y. Z into dou p by dou y. So partial derivative of p with respect to y is s. Therefore z into s plus p into derivative of z with respect to y is q divided by c square equal to 0. When you differentiate partially with respect to y, 0 plus z into s plus p into q by c square equal to 0. By rearranging, 0 into c square is 0, therefore zs plus pq equal to 0. That is the required PDE. Z into s, s means dou square z by dou x dou y, plus p means dou z by dou x, q is dou z by dou y equal to 0. So this is the required PDE. Next question. Form the PDE by eliminating arbitrary constants of the equation z equal to x square plus a into y square plus b. When you differentiate partially with respect to x and y, dou z by dou x is p, x square plus a derivative is 2x, and y square plus b is constant. So 2x into y square plus b. And similarly, when you differentiate partially with respect to y, q equal to y square derivative is 2y 2y into x square plus a. This is constant into 2y. Therefore, 2y into x square plus a. Now, just multiply p and q. pq equal to 2 into 2, 4 x y x square plus a into y square plus b. But x square plus a into y square plus b is nothing but z. And hence, pq equal to 4xyz. That is the required PDE. pq equal to 4xyz. So, x square plus a into y square plus b is nothing but z. So, this is the required partial differential equation. Next question. Find the differential equation of all spheres of fixed radius having their centers in xy plane. If the center is in xy plane, then z coordinate of the center is 0. So, let it be a, comma b, comma 0. This is center of the sphere. Here a and b are arbitrary constants. And fixed radius means assume that r is fixed, radius of the sphere is r. Then equation of the sphere is x minus a whole square plus y minus b whole square plus z minus 0 whole square equal to r square. See, x, y, z be any point in the sphere and center is a, b, 0. Therefore, by distance formula, x minus a whole square plus y minus b whole square plus z minus 0 whole square is r square. That is radius of the sphere square. The equation of the sphere is x minus a whole square plus y minus b whole square plus z square equal to r square. Here r is fixed radius and a and b are variables. Differentiating partially with respect to x and y. 2 into x minus a plus 0 plus 2z into dou z by dou x, that is p, equal to 0. 2 times of x minus a, derivative of x minus a whole square with respect to x is 2 times of x minus a plus, treat y constant when you differentiate partially with respect to x, so it is 0, plus 2z into dou z by dou x, that is p, equal to 0 because r is fixed. And similarly, when you differentiate partially with respect to y, 0 plus 2 times of y minus b plus 2z into dou z by dou y, that is q, equal to 0. Now cancel 2 and then rearrange. X minus a becomes minus zp, y minus b is minus zq, and then square it. X minus a whole square becomes minus square is plus z square p square, and y minus b whole square is z square q square. Now substitute these two in this equation. So you will get PDE. Z square p square plus z square q square plus z square equal to r square. So this is the required partial differential equation. Or you can write z square into p square plus q square plus 1 equal to r square. So this is the required PDE. Next one, form the PDE by eliminating the arbitrary constant a and b of the equation x minus a whole square plus y minus b whole square equal to z square into cot square alpha. Here alpha is fixed constant, a and b are arbitrary constant. Now differentiating partially with respect to x and y, we get 2 into x minus a equal to 2z into dou z by dou x, that is p, cot square alpha, that is constant. So 2z p cot square alpha. And similarly 2 times of y minus b equal to 2zq into cot square alpha. Z square derivative with respect to y is 2z into dou z by dou y, that is q. Now cancel 2 and square. X minus a whole square is z square p square cot power 4 alpha, and y minus b whole square is z square q square cot power 4 alpha. Now substituting in equation 1, we get z square p square cot power 4 alpha plus z square q square cot power 4 alpha equal to z square cot square alpha. Now throughout dividing by z square cot power 4 alpha, we get p square plus q square equal to z square cot square cancels, 1 by cot square remains, that is tan square alpha. Therefore, required PD is p square plus q square equal to tan square alpha. Next question. Form the PD by eliminating the arbitrary constant of equation z equal to a log b into y minus 1 divided by 1 minus x. Now you can write this z as a into log ab by c is log a plus log b minus log c. Therefore, it is log b plus log y minus 1 minus log 1 minus x. Now differentiate partially with respect to x and y. When we are differentiating partially with respect to x and y, we get p equal to a into 0 plus 0 minus 1 by 1 minus x into derivative of minus x is minus 1. Therefore, it is a by 1 minus x. I will repeat once again. Dou z by dou x is p, a into log b derivative with respect to x is 0, log y minus 1 derivative with respect to x is 0, log 1 minus x derivative is 1 by 1 minus x into derivative of 1 minus x, that is minus 1 minus minus plus 1 by 1 minus x. Outside a is there, therefore p becomes a by 1 minus x. And when you differentiate partially with respect to y, q equal to a into 0 plus 1 by y minus 1 minus 0, and hence q becomes a by y minus 1. Just divide these two. P divided by q, p divided by q, a cancels, 1 by 1 minus x divided by 1 by y minus 1, or 1 by 1 minus x into y minus 1. So p by q is y minus 1 by 1 minus x. Now rearrange. P into 1 minus px equal to qy minus q. So p into 1, that is p, minus p into x, that is px, equal to qy minus q. Now rearrange. P plus q equal to px plus qy. So that is the required PD. P plus q is px plus qy. How we can find the partial differential equations? By eliminating arbitrary constant of the given equation. Now in the next lecture, I am going to discuss how we can form the PD by eliminating arbitrary functions. Thank you for watching.